Okay, so hello everyone. So I hope you're enjoying this online conference. Actually, it was mostly Adrian's idea to only put 2 talks a day with a good break so that we can have some questions and discussions with the speakers. So I hope everyone's pleased, and let's give now the the opportunity to George to give his second lecture on vanishing theorems, slope estimates, and control theorem.
Okay, thank you very much. All right, so I guess, right, so I start by talking about vanishing. So let me just begin with the result. Well, Vincent has already mentioned the result, but I remind you. So the theorem is that this finite slope overconvergent cohomology is concentrated in degrees 0 up through the length of this element W. And we also, sorry, and I've made the same mistake that Vincent did, but fixed, and now I fix it too. This is for the cuspidal cohomology. And so what that means is that we take, we use the cuspidal sheaf, bk minus d, where where this d is the boundary divisor. So we take the cuspidal sheaf, and we have a conjecture about the non-cuspidal sheaf, which we can't prove at the moment, but it's probably not too hard. Well, maybe not too hard, which is that this sort of the dual thing, it's concentrated in degrees length of W up through the dimension. Okay, so I want to explain to you how this is proved. And but before I do that, I want to just give some examples, which are going to hopefully clarify what these cohomologies with support look like, and hopefully make you less confused about the thing that I rather hastily talked about at the end of last time, talking about support conditions on the flag variety. So let me begin with a sort of very concrete example, which is more or less the key to proving this theorem in some sense. So let's consider a product of two Tate disks sitting inside a product of two Tate disks, one of which is larger, but the other isn't. And maybe you can think about this as all sitting inside the adics A2. And okay, so what I want to consider now is the closure of this sort of smaller polydisk inside the bigger polydisk. And when I say the closure, I mean in the sense of the underlying topological spaces of adic spaces. And as in the last talk, this is what's always confusing, is that we say closed Tate disk, but of course they're actually open in the sense of the topology of the adic space. So I take the closure, and this is the closure inside this bigger polydisk. And let me call this Z, and let me call the bigger polydisk U. And so the picture is that we have maybe the small polydisk, which I picture as kind of a square, sitting inside the sort of bigger polydisk, which is sort of bigger in one direction, but not in the other. And we're kind of taking this partial closure where we sort of add maybe some non-classical points at both of the ends. And let me call the complement V be U minus Z the complement. And so this is just this disk times a sort of half-open annulus, which is sort of, oops, that's not how you spell annulus, which is sort of having sort of open on the inside and closed on the outside. Well, anyways, it doesn't really matter. So this half-open annulus, which is also a classical rigid analytic space. And so the point is, again, this is a basic example of a non-admissible cover. So here we have our sort of Z, and I guess our V is kind of split up into two pieces because of the way I've drawn it. So if you take V and the smaller polydisk that we started with, they contain all the classical points of the bigger polydisk, but they're not an admissible cover. And so when we take, from the point of view of adic spaces, there's some kind of higher rank points which are not contained in either of them, and we're sort of putting them in the closure Z, okay? And this is the example of the kind of thing that we could use when we're taking this cohomology with support on adic spaces. So the question is, or rather the claim is, that R gamma Z U of F for F a coherent sheaf has amplitude 0, 1. And the proof is very easy. I've basically told you how to compute cohomology with support by using this triangle. So we have this triangle R gamma Z U F goes to R gamma U F goes to R gamma of the complement VF. And now the claim is that both of these have no higher cohomology. And for U, well, U is literally an aphanoid, but so V is not quite an aphanoid because of this sort of open radius part. And it's also not a Stein space, but in fact, it's what's called a quasi-Stein space. And it's the sort of space in which one has this sort of theorem B in rigid analytic geometry, so that there's no higher coherent cohomology. So theorem of Kiel. So in particular, from this triangle, we now get that this is in degrees 0 and 1. And just to generalize this example a bit, and more or less get the thing that we need to prove our theorem, let's just add more coordinates. So I can consider sort of d1 to the a times d1 to the b sitting inside d1 to the a again, but then the larger disk to the b. And I do the same thing. I take the closure. So now we're kind of closing up this polydisk in kind of b different directions inside the bigger polydisk. And now what's going to happen? This cohomology with support in degrees 0 up through b. And the way to see this is we're going to use this triangle. And now we have to consider the cohomology of the complement, R gamma V. And now the point is V is no longer going to be quasi-Stein, but it's in degrees 0 through b minus 1, because V is covered by b quasi-Stein opens, which have no higher cohomology. So we have a check cover with no higher cohomology, an acyclic check cover by b things. And the way you do it, I'll just draw the picture for b equals 2. You have maybe the bigger polydisk and this sort of closed up smaller polydisk. And the way that you cover it is you take sort of an annulus times a polydisk in one direction and an annulus times the polydisk in the other direction. So that's a check cover with two acyclic things. So you see that there's not going to be any H2 or higher. Okay? So hopefully that kind of clears up a little bit what these kind of cohomologies with support looks like. And the thing that I just want to emphasize is that in all these examples, U itself was affine or aphanoid. And all the higher cohomology is really coming from the fact that V is not aphanoid. Okay, this sort of complement of the closed is not aphanoid. Okay, so now let me sketch the proof of the theorem. So first of all, there's this thing that Siegel asked about at the end of last time. Well, we're going to use the affineness of the Hodge-Tate period map. So we have our toroidal compactification. We have now the minimal compactification, and we have for both of them Hodge-Tate period maps. And let me call this map pi. And so the point is, the reason that we need to consider the cuspidal sheaf is that it's this map which is affine. And of course, the map from the toroidal compactification to the minimal compactification is not affine. Anyways, if you don't like this bit about compactifications, it doesn't really matter, just ignore it. And so the point is, what are we going to do? We're going to use the theorem of Harris, Lund, Taylor, and Thorne, and independently Andreatta, Iovita, and Poloni, which says that when you take this cuspidal sheaf, but not for the sort of non-cuspidal sheaf, there are no higher direct images. So now we can work on the minimal compactification and now use the affineness of the Hodge-Tate period map. So that's one thing we use. We use the affineness of pi Hodge-Tate in a suitable sense, which I'm not going to carefully recall. And we use the description of support conditions, as I will just remind you in a sec what they look like, but they look, sort of on the flag variety. And then we use the computation in the example, because in fact, the computation that I did in the example is exactly what somehow the support conditions on the flag variety looked like. So let me just remind you how that goes and explain where the length of W comes from. So, let me just remind you that I had described these sort of partially closed polydisks inside the flag variety in terms of some root subspaces. So we had this sort of thing that I called CWFP, and then there were some parameters M and N, and it is somehow described using some balls in root subspaces with some sort of big indexing sets, which I'll just write, but you can just sort of ignore if you don't want to think about them. But the point is that this is just a polydisk. And then what we did is I also defined this partially closed version, and I can define it in a way which looks more like the examples above. Namely, I can view this polydisk as sort of sitting inside a slightly bigger one in the sort of n direction. So I've sort of made it bigger in the kind of n directions. And I take now the closure, but sort of inside this bigger polydisk. And this is the thing that I've just defined last time as CW, FP, M, and bar, this sort of partially closed polydisk. And now we were exactly sort of taking cohomology with support where this is Z and this is U, okay? And so it's exactly like in the example. The only thing we need to do is understand what is the cardinality of this indexing set, which is kind of the number of directions that it's closed in. And
could you remind me how general the M and the N are supposed to be and why they're
supposed to be rational. Other than that, it doesn't exactly matter. Although, yeah, except that there's some technical point that I'm ignoring, which is that we might have to take them kind of big. Right, so there's a subtlety in what it means that the Hodge-Tate period map. I mean, okay, so to find these regions, we need to assume that M and N are rational.
Mm-hmm. And I mean, do they come from the actions of successive Heck operators, or is there some?
Well, yeah, so the Heck operators will kind of grow and shrink them, but for now they can just, I mean, the point is that by this analytic continuation argument, you could actually kind of use just about any of them, as well, maybe at least as long as the parameters are sufficiently large. But yeah. Okay, so the cardinality of the set, well, it's really the same as the cardinality of just W inverse phi minus intersect phi plus, which is sort of the usual definition of the length of W. And the reason that this equality is true is that W is in this set of constant representatives. And one of the ways I told you last time to interpret this is that sort of W sends phi plus, W of phi plus contains all the sort of M positive roots. So in particular, it doesn't matter if in the negative roots, I'm including the roots of M or not. Anyways, so, okay, I hope by explaining things that way, it's kind of clarified a little bit what these cohomologies with support look like, and well, also explained why the theorem is true. Okay, so now I want to talk about slopes. Well, and eventually classicality. And for this discussion, I'm eventually mostly going to specialize to the case of GL2 and GSP4, so we can actually see some formulas and make things as concrete as possible. So let me first just recall the general theorem and explain exactly what it means. So let's introduce some notations. So if we take a character of this monoid, which we should think of as being a sort of system of UP eigenvalues, then we're going to define a rational, so we want to take the sort of valuations of the UP eigenvalues. We want to take the valuations of the UP eigenvalues and view that as a sort of rational character of our torus, just by the formula that if you pair this co-character, this valuation, with a co-weight mu, that's equal to the valuation of lambda of mu of p. I'm sorry if this is all a little bit confusing, but I just want to explain the notation that Vincent used in his first talk. Okay, so we're just taking a system of UP eigenvalues and taking its valuation, taking their valuation. So V of lambda is basically like a slope of a finite slope modular form. Okay, and there's a partial order.
George, did you write mu of p?
Yeah, so mu is a co-character.
So
I plug in p into the co-character to get an element of the torus, and then I apply lambda to it.
okay.
And okay, so maybe this is a little bit imprecise. I mean, of course, maybe I should have just written T of QP instead of T plus. The point is, it doesn't matter. It's a monoid, but the monoid generates T of QP. Sorry. Anyways, there's a partial order less than or equal to on this group of rational co-characters, which is just the usual thing. So say nu is bigger than or equal to 0 if nu can be written as a sort of rational, positive rational linear combination of simple roots. Okay, and so with this slightly cumbersome notation, we can state a theorem and a conjecture. Well, maybe I'll state the conjecture first and then the theorem about what the slopes on these overconvergent cohomologies can be. And really, this is just a way of packaging the statement about all the different Hecke operators together at the same time. So, so the conjecture is that any system of Hecke eigenvalues lambda from T plus to QP bar cross occurring in one of these overconvergent cohomologies. So for a given W and a given weight kappa, what satisfies V lambda is bigger than or equal to, well, I just write again this formula that Vincent wrote, kappa plus rho, where
maybe minus rho or plus rho, what? Oh,
no, really plus rho. Don't think too hard about this formula, okay? I'm going to explain more concretely. I'm going to write actual formulas later on. So yeah, I agree that it looks very weird. that it's a plus row rather than a minus row, but it is the right thing. So W naught M in W, Wn is the longest element, and rho is half the sum of the positive roots. And then the theorem, the thing that we actually prove, is the slightly weaker inequality. So it's a worse lower bound, which is just this. Okay, and I'm going to tell you, don't stare too hard at these formulas because, I mean, I'm going to write them in a more concrete way for GL2 and GSP4 later. But anyways, so let me make some remarks. So first of all, I mean, let me just say that equality in the conjecture corresponds to being ordinary. So ordinary means something that sort of the slopes are as small as possible. And that should be the, and those slopes are equality in the conjecture. And so in particular, that's why we're 100% sure that the conjecture is correct, because you shouldn't have things with slopes smaller than the classes which are supposed to be ordinary. The next remark is that the difference between the conjecture and the theorem is related to analyzing the sort of trace of P1 part of the definition of the Heck operator. And that's something that's a little bit tricky. So, I mean, somehow the idea is that if you think about what is a Heck operator, to get the value of the Heck operator of the modular form at some point, you're sort of summing up some values at some other points. And so we're doing some estimation of each of those individual points to see how integral they are. But then we're failing to see the sort of extra integrality coming from the fact that there's some cancellation when you sum them up. I'll say maybe a little bit more about that as we discuss specific examples. And then the third remark is that if you want to make this kind of statement more concrete, let me just say that another way of describing this inequality is just to say that somehow well, first of all, the restrictions to the center are the same. And somehow you can test it on fundamental dominant co-weights. So sort of mu of pi I is bigger than or equal to mu of pi I prime, where pi 1 up through pi g are the fundamental dominant co-weights. And so really, I mean, all these slope bounds that we're going to write just express some conditions that you can state in terms of sort of a collection of Heck operators corresponding to the fundamental dominant co-weights, which is the way that you usually find these slope conditions stated, and is probably more concrete. So, e.g. for GSP4. Sorry?
The prime should be on mu, not on pi.
Ah, I'm sorry, yes, you're right. Thank you. So for GSP4, for example, I mean, we just have bounds on slopes for example, the two Heck operators corresponding to fundamental dominant weights. So for example, UP1, which is maybe this one, and UP2, which is maybe this one, okay? All right, so let's try to understand more or less how this is proved. So the strategy so first of all, if you want to prove a bound for the valuations of the eigenvalues, so so if maybe we have an endomorphism of a QP vector space, to prove that valuations of the eigenvalues of T are greater than or equal to C, we can find a lattice L inside V so that T of L is contained in P to the C of L. Okay, so that's what we'll do. And so we need to find somehow a lattice in these overconvergent cohomologies. So to do this, we will consider some kind of, first of all, lattices in the sheaves that we're taking cohomologies of. So some kind of OSK plus subsheaf, VK plus inside VK, which is somehow sort of an integral structure on the sheaf. And to find these, well, so the V kappas are obtained from the Hodge bundle by Schur functors. So that maybe I should just remind you, the Hodge bundle is sort of the pullback along the identity section of the sheaf of differentials for the universal abelian variety. So E is sort of the identity section. And so it suffices to find this lattice or this integral sheaf for E. And we get E plus inside E using integral differentials, at least sort of on the good reduction locus. Yeah, and actually, maybe here I should say that the way that I'm going to explain this proof is actually a little bit different than the way we wrote it in our paper, but is maybe more similar to the way that we wrote it in the paper we wrote for GL2. But, well, I think it's a little bit more comprehensible to explain like this. So, okay. And now we have to start thinking about cohomologies with support. So how does this work? So recall that this R gamma W KP kappa is computed as some cohomology with support R gamma U intersect Z U V kappa, where we have some support conditions. So U and open, sorry, not V, but Z. Z is closed. And sort of the point is that where U intersect Z is a small locally closed neighborhood, which we can make as small as we want, of this component of the ordinary locus, which I'm going to call SK ord W, which is this sort of pi Hodge-Tate inverse of P W KP. Well, at least up to some higher rank points, but I'm never actually going to do anything with this. So it doesn't really matter which, I only care about the classical points anyways. Okay, so this component of the ordinary locus. And so what we need to do is we need to study somehow what the correspondence looks like on this component of the ordinary locus. So we have our sort of Hecker correspondence. And as an ingredient in this Hecker correspondence, we had a map of sheaves. So in a neighborhood, but we show that on P1 inverse SK or W intersect P2 inverse SK or W. This is sort of like the piece of the correspondence that is sort of fixing this component of the ordinary locus. So the piece of the correspondence which is going from this component back to this component. We have a factorization as follows. So we have this map of sheaves living over the correspondence, which we use in the definition of the action on cohomology. It's supposed to be a 1. And so inside that, we have these kind of integral structures on the sheaves. and this is the thing we're trying to study. And we show that there's a factorization with p to some power. And well, the point is to figure out what that is. And so we deduce from that on this slightly bigger region, P1 inverse U intersect P2 inverse Z, we have, well, basically the same thing, but just with a little loss because the region is now slightly bigger. So P to the C minus epsilon. Where this epsilon greater than 0 can be made as small as possible by shrinking this locally closed U intersect Z. And so the idea is we really only have to understand what's going on over the ordinary locus anyways. And that's actually, as I'm going to explain in a sec, not a very hard problem. So let me just remind you of the picture so that you understand like what is the significance of these sets, these sort of intersections on the correspondence. So this is just the picture of how correspondence acts on cohomology with support. So we have this component of the ordinary locus, SK ord W that we're trying to study. And then we have maybe our open set U, and we have our closed set Z. And so the point is when you look at the action of the correspondence, there's some part which is sort of staying on the piece that we care about, but then there's also allowed to be stuff which is sort of leaving and stuff which is coming in. But the rule is that the stuff which is coming in has to be coming in from outside of the set U. And the stuff which is leaving has to be leaving the set Z. And that was the sort of requirement to even get an action on cohomology in the first place. And so what it means is that when we define the action of this Heck operator on cohomology, sort of this part and this part just didn't even contribute. And the only part which mattered was this kind of fixed part. And that's exactly what we're studying up here, well, on these regions. Okay. So now basically we have to figure out what C is. Okay, and I just want to do an example for you so you can see what kind of problem this is. So let's do it for the correspondence UP. So for sort of UP, by which I mean the thing that we might call UPG, or in other words, the Heck operator associated to the matrix sort of ones and then P inverses. This is what people classically call UP in the theory of Siegel modular forms. And let's do it for GL2 and GSP4, but you'll easily be able to generalize it. Okay, so let me first of all describe what is this correspondence UP. So let me give the moduli interpretation. So first of all, let me remind you that my Shimura variety with Iwahori level is the moduli of triples A lambda, and then the Iwahori level structure HI. So A and lambda is a principally polarized abelian variety of dimension G, and this sort of Iwahori level structure is a symplectic flag in the P torsion, a complete symplectic flag. And what is the correspondence? Well, the same stuff as before, but now we add another subgroup L. So A, lambda, and HI are as above. And what is L? Well, L inside the P torsion of A is a maximal isotropic subgroup. And it should be disjoint from the middle piece of the Iwahori level structure. Okay? So that's the definition of the UP correspondence on the Iwahori level Shimura variety. And I guess I should tell you what P1 and P2 are. So P1 is just sort of forget L. And P2, you quotient out by L. Take the sort of induced polarization in Iwahori level structure, where the induced Iwahori level structure is defined by hi plus L mod L, at least for I sort of from 0 to G, and then you just take orthogonal complements to get the rest. Okay, so that's the definition. All right. The last thing is I should, of course, tell you what the map at the level of sheaves is that we want to investigate. But of course, it's just pull back on differentials. So over the whole correspondence C, we have a universal isogeny, sort of a universal isogeny A going to A mod L. And so if we take the induced map on differentials, we get a map sort of from the Hodge bundle of A mod L to the Hodge bundle of A. So this is P1 upper star of the Hodge bundle on the Shimura variety, and this is P2 upper star of the Hodge bundle on the Shimura variety, and this is this map that we're using to define the Heck action. And of course, we take Schur functors applied to this to get the ones for all the other automorphic sheaves. Okay. So now let's do GL2. Maybe I start on a new page because I want to draw a picture. So I remind you that the picture for GL2 of X naught of P, we have sort of two components of the ordinary locus. Okay, and these can be described in terms, I mean, they can be described in terms of the interaction with the canonical subgroup. So the canonical ordinary locus is the one where the Iwahori level structure is the canonical subgroup, and then the anti-canonical locus is the one where the Iwahori level is not equal to the canonical subgroup. And what does UP look like? Well, if I just draw UP on the ordinary locus, there's a kind of fixed piece here, a piece going like this, and a fixed piece here. And I can describe for you what all of these mean. So this piece is where I take L to be the canonical subgroup, which is allowed because H is not the canonical subgroup. And then you stay on the anti-canonical locus. And then these two pieces are where you take L to not be the canonical subgroup, because as you can easily check, if L is not the canonical subgroup, then the new Iwahori level structure is always the canonical subgroup. So this is the sense in which, well, one sense in which sort of the canonical ordinary locus is kind of like an attracting fixed point for UP. But we've only talked about the ordinary locus here. Okay, so now let's do the computation that we're supposed to do. So on the W equals 1 piece, this fixed part, namely, so the pieces we have to analyze are these two fixed parts like this. So on W equals 1, we're quotienting out by something which is not the canonical subgroup. So the isogeny is sort of integrally étoile. And so that means that the map on differentials is integrally an isomorphism. And so what we get is that the slopes are just bigger than or equal to 0. And in fact, that's not the correct answer. The correct answer, at least according to the way that I've normalized, is that the slopes are bigger than or equal to 1. And okay, so usually people divide, I mean, my UP operator here is P times the usual UP operator. And usually people divide by P precisely for the reason that it's actually bigger than or equal to 1. And of course, that's somehow coming from the fact that we're summing up P different values. And when we take this trace, it's, I mean, this map P1 looks like Frobenius in characteristic P. Okay. And that's sort of an example of the difference between the theorem and the conjecture already. Of course, here we can prove the theorem easily. So on the W naught guy, e to e mod L is Frobenius, is a Frobenius lift. And so what that means is that the map on differentials looks like sort of multiplication by p. And so now if you take the k tensor power to get into weight k, you'll get that the slopes are bigger than or equal to k. Okay? And so these explain how we prove the slope bounds in this case. And then I guess Vincent already explained how you deduce Coleman classicality from the slope bounds. So I won't do it, but I'll do it for GSP4. Okay, so let's do GSP4. And now I'm going to remind you, or probably tell you, what this set WM is and what the meaning, the modular interpretation is. So let's first of all introduce the simple reflections, just to write down some elements.
Can I just ask?
Yeah.
This little gap between what's expected and what you prove in terms of slope bounds.
Yeah.
Is that the difference between small slope and strictly small slope in the theorem?
Yeah, exactly. Yeah. Exactly.
Thank you.
All right. So there's S1, which is 1, 2, 3, 4. Anyways, well, I'm going to write them, but it doesn't really matter that much. And so now WM is just the Z mod 2Z generated by S1. And then the set WM has 4 elements, and it's basically all the things that start with S2. So S2, S2, S1, and S2, S1, S2. So there's 1 of each length from 0 to 3. Okay, and as David asked me last time, I can tell you concretely what the meaning of each of these components are. So SK or W corresponds to ordinary abelian varieties with Iwahori level structure in a certain relative position with the canonical subgroup. And this element W is just telling you what the relative position is. So let me just even make that more concrete by telling you how it works. So let me draw a table. Well, I'm going to actually be drawing lots of tables.
So George, you're considering Hecke correspondence where the basic level is Iwahori level?
Yes.
Huh. That's weird that you have so many components in that. Okay.
Well, I'll tell you what the meaning is right now. So, I mean, the most special position you could be in, which corresponds to 1, is that H2, the middle guy of your Iwahori level structure, is the canonical subgroup. And of course, that forces this dimension to be 1. The next most general thing is that H1 is contained in the canonical subgroup, but then that's the only intersection with H2. The third most general thing is that H1 is not in the canonical subgroup, but there's still some intersection with H2. And then the most general position would be that H2 doesn't meet the canonical subgroup, okay? So that's the description of these 4 components. And now we need to understand somehow on the fixed part, what does the map on differentials look like? And I'm going to explain to you one way to understand that. So I'm going to prove a little lemma, which I might call the sort of maybe what I call like the ordinary dynamics or something. And I just want to say that, I mean, one can understand all of these things using the Hodge-Tate period map, but in some sense, I view that as kind of silly overkill when you're just studying ordinary things where everything is completely elementary. So that's why I explain it this way. So what does the lemma say? So let's take a point A lambda HIL be a say, classical point of this Hecker correspondence C with good ordinary reduction. Of course, if, yeah, so that by that I mean A has good ordinary reduction. So now, then we have some inequalities. So the dimension of H2 intersect the canonical subgroup is less than or equal to the dimension, sorry, it's less than or equal to 2 minus the dimension of L intersect the canonical subgroup is less than or equal to the dimension of H2 prime intersect H can prime. So let me explain what everything is here. So I remind you that we have this isogeny of abelian varieties, A goes to A mod L, and we have the map on P torsions, L being the kernel. And then in each of these, we have two subgroups. We have the canonical subgroup, and we have this Iwahori level structure H2. Okay, and so what this lemma says is it's saying a couple of things, but if you ignore this term in the middle and just look at the two terms on the outside, it's saying that as you apply UP to ordinary points, H2 can only become more canonical. And of course, that's what we kind of already understood by thinking about the action on flag varieties, but okay, this is some other way to understand it. And I should say that, but the real reason that we care about this is then in the situation that the two endpoints are equal, meaning that you're not actually getting more canonical. So if you're sort of staying on the same W, if the W is staying the same, then we know somehow what kind of subgroup L is. In particular, we know how sort of multiplicative or atal it is, and that's going to tell us what the map on differentials looks like, which is what we want to compute C. Okay, so I hope you understand why I'm proving this lemma. So let me just prove it. I hope I can prove it because it's just elementary algebra in some sense. So the point is we have that if you consider the canonical subgroup plus L divided by L, that's a subgroup, and I'm going to view that as a subgroup of this. Well, that's actually in both of H can prime and H2. It's in H can prime because H can maps to H can prime. There might be a kernel. It's not necessarily subjective, but it does map to it. And it's in H2 because in fact, H2 is the image of this map. That was sort of the definition of this new Iwahori level structure. The middle guy is just the image of this map. So it's in their intersection. And on the other hand, something that's obviously inside this is the intersection of H can with H2 plus L mod L. And now let's compute the dimensions of everything. This is isomorphic to, well, I mean, it's isomorphic to H can intersect H2 because the intersection of L and H2 was assumed to be 0 in the definition. And this is isomorphic to H can mod L intersect H can. Okay, and now you just take the dimensions and you get the formula I've written up there. Okay. So hopefully that wasn't completely incomprehensible nor completely a waste of time, because I think it's good to know how to prove this lemma in life. Okay. Even though, yes, you could also read this off from the Hodge-Tate period map. So what does this tell us about the maps on differentials for the sort of fixed parts? So we get a new table. Sorry, S2. And so the first thing that I'll write is the dimension of L intersect H can. Oops. That's not how tables work. Sorry. Ah, oh God, what has happened? Yeah. Sorry, I'm not very good at this and I keep hitting the wrong thing. So here is the dimension of L intersect H can. And so I guess it's just 2 minus the thing in the table above. So it's a sort of 0 because this one will be a tall 1, 1, 2. And then we want to write down a sort of what the map on differentials looks like. So the map sort of P2 upper star or the map. Oops. Sorry, I'm getting a bit stressed out and it's making me make weird mistakes. So we want to look at the map on differentials. And so here it's a tall, so in some suitable basis for the integral differentials, it looks like that. Here it's going to look like P and 1, and here P and P. Okay, so now for K1 bigger than or equal to K2, we consider the sort of automorphic vector bundle sim K1 minus K2 of the Hodge bundle, tensor the determinant of the Hodge bundle, determinant to the K2 of the Hodge bundle. And we want to use, basically take this symmetric power times determinant of each of the matrices and ask what's the smallest valuation of one of the entries. And that gives us our slope bound. So I'll write what's probably the last table of my talk. Sorry, it's 2.
You should use the rule of good notes for this.
Okay, I don't know anything. Sorry. So so this is this Heck operator UP2. I'm going to write in a second the lower bound for UP1. So for example, here we get 0 because, well, everything is the identity. Here we're going to get K2. We get nothing from the symmetric power because that will have 1 as an eigenvalue, but we get a K2 from the determinant. Here we also get a K2. And here we get a K1 minus K2 from the symmetric power and a 2K2 from the determinant. So we get K1 plus K2. Okay? And so what you see from this table is that you already get a classicality theorem, for example, for overconvergent modular forms. Because, for example, when K2 is positive, if this number K2 is positive, then by asking that the slopes be less than K2, all of these terms are going to be killed in our spectral sequence, and only the term corresponding to overconvergent modular forms will be left. On the other hand, if you want a classicality theorem for the theory corresponding to this guy of length 1, what I've written for you isn't good enough. By putting a condition on UP2, you'll be able to kill this term in a suitable range of suitable values of K2. But of course, you have no way to kill this term because this number is the same. Okay? So you clearly need to use the other Heck operator. And so let me just go ahead and write the answer. So I leave it to you as a very good exercise to try to run the procedure I did above to get the slope bounds for the other Heck operator. And I'll just write the answer. So it's K2, 2K2 plus K1, 2K2 plus K1. And you notice that, again, here you see the same value twice, and here you see the same value twice. In fact, I mean, you can kind of guess why this was the case. I mean, in the computation we did above, only H2 mattered for the dynamics of this Heck operator UP2. And that's why you got the same numbers here. And similarly, only H1 matters for the dynamics of UP1, and that's why you get the same numbers here. Anyways, in case you're wondering why it works like that. So, okay, so these are the numbers of the theorem, and let me go ahead and also write the numbers of the conjecture in blue. So I write how to change them. So all the numbers, or some of the numbers, get a little bit bigger. So we get a 3 here, a 3 here, a 1 here, a 1 here, and a 3 here. Okay, so some of the numbers get a little bit bigger, and then these last 3 over here stay the same. So these are the correct values. And of course, we can prove this again for overconvergent modular forms. The problem is having to do with higher cohomology. So the stuff in the, well, yeah. Okay. So now let's, so from this, we get some classicality theorems, and I'll maybe just start writing them. I don't want to write them all because that will actually take a while. So we have, for example, that R gamma W KP kappa question mark, where I'll write below what question mark means, but it'll be a slope condition, is isomorphic to the classical cohomology question mark 4. And so, for example, when W equals 1, you get this classicality theorem, well, when K2 is bigger than 3, under the slope condition that UP2 is less than K2, right? That's exactly what this table is telling us if you ignore the blue. And the reason I say K2 is bigger than 3, of course, I could have just written K2 is bigger than 0, but the point is that this is only non-vacuous when K2 is bigger than 3, because we know that the lowest this slopes can be here is 3. So if you want the theorem to actually apply to any modular forms at all, in particular like ordinary modular forms, you're going to have to assume that K2 is at least 3. And if you assume the conjecture, you get a slope bound which is slightly improved. So you can improve this to greater than 2, not much better. And you can improve this to K2 plus 1. And that's the correct classicality theorem. That's what should be true. And you shouldn't expect anything better than that. And maybe I also write the one for W equals 1. W equals S2. So now the condition is K2 is less than 0, and K1 plus K2 is bigger than 3. And we put slope bounds on both of the Heck operators. So UP2 is less than 0, and UP1 is less than 2 K2 plus K1. And again, I'm just reading this all off from the table because somehow the 0 is here, and the 2 K2 plus K1 is here. So I'm using somehow this condition to kill this guy, and I'm using this condition to kill this guy and this guy. Okay. And again, this improves slightly if you assume the conjecture. So you can put a 2 here instead of a 0, and you can put I guess you can put a 3 here instead of a 0. And so let me conclude by just drawing a picture of the sort of K1s and K2s. So I'm going to draw it in a sort of funny way like this. So here the x-axis is K1, the y-axis is K2. And let me label the equations for all these lines. So here we have K2 is 2. I really should be able to remember these, but K1 plus K2 is equal to 3. K1 is equal to 1. And this dotted line, which is sort of not allowed, is K2 is K1 plus 1. So the weights, we're requiring that K1 is bigger than or equal to K2, which is sort of 1 off from this line. And so along 1 off from this line, you have the sort of scalar weights. So for example, here is 2, 2, here is 3, 3, etc. So this is the sort of line of scalar weights, which is 1 off from the dotted line. And so what you see is that the walls in this picture, which are what correspond to irregular weights, are exactly when you have a tie between 2 terms in the slope bound. So like, for example, along this wall here, K2 equals 2, which is sort of where the sort of holomorphic limits of discrete series live. You see that this number 3 is equal to this number K2 plus 1. And again, these 2 numbers are equal. And so there's no way you're going to distinguish those 2 theories apart on that wall. And indeed, classically, you have, in the classical cohomology, you have cohomology sort of in both degrees 0 and 1. And sort of similarly for sort of this wall here, you again have a tie. And for this wall, you again have a tie. And so you can label the chambers by the elements of the Weil group. And in the interior of the chambers, at least assuming the conjecture, you get a classicality theorem that's strong enough to prove that ordinary classes are classical for any weight in the interior. And if you only have the theorem, which is slightly weaker, you have to put some slightly stricter regularity conditions. Like, for example, the correct thing would be K2 bigger than 2, which exactly corresponds to just being in this chamber. But then we actually saw that what we actually got was K2 bigger than 3, which means that this guys, which are one off the wall, are kind of also bad. Anyways, is there anything else I even want to say about this? I mean, we can always have a discussion, so maybe I stop there.
Okay, let's thank George for his talk.
May I ask a question?
Go ahead, Michael.
All right. So I understand that the W's parameterize the Schubert cells, and they also parameterize the configurations relative of mu p's and étal Z mod pz's in the level structure, but they also parameterize the different kinds of discrete series.
Yes.
And so is there a more or less a bijection? Does this, that's the first part of the question. The second part of the question is, are all these cohomology computed ultimately by H0s on aphenoids, or on something that's maybe I mean, ultimately by coverings by quasi-Stein spaces, or I mean,
so let me address your first question. So yes, the answer is yes, and in some sense, what the sort of classicality thing, I mean, in some sense, you should be thinking that somehow each of these different, when we talk about interpolation tomorrow, or when Vincent does, each of these different overconvergent cohomologies is somehow giving you a way to p-adically interpolate each of the different families of discrete series or limit of discrete series representations. And that connection, of course, is made by the classicality theorem, because you know that these discrete series, series are showing up in here. And so they're thus contributing to this overconvergent cohomology by the classicality theorem. As to your second question, well, I mean, the answer is, of course, I mean, you can always compute everything by covering it with affines, but I mean, it's not really clear. But basically, I mean, the problem, if your question is, so in all these old works where we constructed congruences, and we ultimately constructed congruences with holomorphic things by doing things like taking coverings or by using some Hasse invariant stuff, yes, that was all well and good, but the problem is that it was never very useful for chasing Heck operators at P through the calculations. Like, all those computations of higher cohomology were rigged to be compatible with Heck operators away from P, but incompatible with Heck operators at P, which sort of hurts their usefulness. So I think Vincent is going to explain that sort of one application of this is that you can prove some kind of local global compatibility for the Galois representations associated to limits of discrete series, that you could construct those Galois representations before, but you didn't know how to prove this local global compatibility. Yeah, I don't know.
Okay, no, that was not why I was asking the question. I asked Vincent. Okay. I asked Vincent a specific question yesterday, but that's I think I should take it up with him then.
Okay.
Okay. Are there other questions?
I have a question, if I may. It looks like there is indeed a lot of progress here in understanding these local cohomology groups, and but everything is done by taking finite slopes. So it seems to me that there is a more and more interest in understanding what happens in infinite slope case. So for example, one can think about kind of a partial infinite slope, right? I mean, we have various heck operators. Can you say anything, or I mean, of course, you haven't thought about it yet, but do you have like an idea if sort of infinite slope things can be at all addressed?
So, well, okay. So as one way to, I mean, you suggested this thing about partially finite slope things.
Right.
So I should say that, I mean, there should be, of course, some version of this theory where this is the theory associated to the Borel, and there's also theories associated to each parabolic, where you sort of, when you consider a parabolic, you're considering things which are sort of finite slope just for the heck operators corresponding to that parabolic, but then you're going to get analytic variation over a smaller weight space.
Right.
So that's one thing that you could be talking about. And then the other thing you could be talking about is, like, for example, this theorem of Louis Pan, where he's proving some kind of thing about Hodge-Tate periods for actually genuinely infinite slope overconvergent modular forms just on the modular curve, which is awesome. And I must confess, I don't really know very much about. I don't know. So which direction are you going in?
I'm in both of them. I mean,
okay, I think the answer then is the first thing, we have some pretty good idea of what it should look like, and the second thing, we have absolutely no idea, but we'd love to learn.
I see. Okay.
Can I make a comment on that?
Yeah.
You said there should be a theory for parabolics other than the Borel.
Yeah.
But I reckon that when you have a parabolic that's not a Borel, there should actually be two theories. One of which gives you a space that's smaller than the Borel thing, with fewer directions of analytic variation, and the other of which gives you more.
Yeah.
So for GL2 and the parabolic being the whole group, you have one theory which should just give you character twists of a fixed thing, but the other theory should be giving you the full unrestricted global deformation space.
Yes.
And there is some. I mean, I have a small preprint and some speculations about this, and there seems to be an emerging picture of these big and small eigenvarieties for non-trivial parabolics.
Yes.
So what you just hinted at was probably the small eigenvariety.
The small one, yes. Yeah.
But there is the big one as well, which I'd like to construct.
I think it's a very interesting thing, and I don't.
Okay, sorry for the interruption.
No, it's a good point, and because it's another way to address Adrian's question, and I don't know anything about that, and it's kind of it's something that's really actually puzzling to me.
Yeah, it is puzzling.
How you're supposed to construct these things you call the big eigenvariety. Yeah. Because I think that it's kind of a point that on the Galois side, it's sort of clear that they exist. And the Galois side is often kind of guiding us in this business for telling us what should exist. So every time you can see something on the Galois side, there should be an automorphic counterpart, but yeah, no one knows what it is, I think. Yeah. Well, there's, okay, sorry.
No problem. Are there some other questions? Okay, if not, let's thank George again, and we'll resume in 3/4 of an hour.